Okay, how fast would you have to throw a snowball in order to completely melt on impact? So what we have is we have the ice cube or snowball thrown against a wall. We have a conversion of energy. So we have kinetic energy, 1/2 mass times the speed squared, and it's hitting the wall, and we're going to have some thermal energy here. So we have a couple of constants that we need. One is what's called the specific heat. And for water, it's 4,200 joules per kilogram degrees Celsius. And what this means is that it takes 4,200 joules to raise 1 kilogram of water by 1 Celsius. We also have what's called the latent heat of fusion, which is the amount of energy to melt 1 kilogram of water, in this case, or whatever substance you're dealing with, for water at the melting temperature. And so now what we have is we have the following. I'm going to keep M as just the name of the mass of the snowball or the ice cube, and we have 1/2 mass times the unknown speed squared should be equal to, and so we need to have a kind of a starting temperature for this ice cube, and let's say it's kind of like out of a freezer, which usually has something on the order of like -10 Celsius. We need to raise the temperature of the block by 10 degrees to get it up to 0, and then we need to dump in enough energy to melt it. So then we have 4,200 joules for every kilogram degrees Celsius. We have times the mass in kilograms times 10 degrees Celsius, and notice the units will work out to be joules. And then we have to add that energy of melting it at that temperature. So we've raised it up, and then now we have to melt it 330,000 joules per every kilogram, and then also times the mass. Notice now that the mass cancels out in every single term. So the mass does not play a role at all. And so the on the right hand side we just have a number. So I can simply say v squared. Let me go back to yellow. V squared is equal to 2 times this whole quantity, and go into a calculator, 2 times 4,200, 4,200 times 10 plus 2 times 330,000. I get a quantity of about 7.5 times 10 to the 5. Excuse me, joules per kilogram, which is also meters squared per second squared. And so now I get a final speed of the square root of this thing, and so I get square root of the answer is about 8.6 times 10 to the 2, or about 860 meters per second, which is, somewhere around 1,800 miles an hour. And notice this, all we're doing is we are, just to summarize, all we're doing is we are taking a certain amount of energy at the beginning, equating it to thermal energy in several steps. We have raising the ice cube up to 0 and then melting it. And if we wanted to ask the question how fast would it have to be to completely vaporize it on impact, then I'd have these same terms, but then I would want to add terms here to essentially raise the temperature up to the boiling rather the kind of the point for vaporization. So basically the boiling point. All right, and then I'd need to add another to actually vaporize it or to boil it. So we'd have another set of energies there. And we could look up the constant. The constant for water is somewhere in the millions, 1.4 million, if I'm thinking about it right, joules per kilogram to vaporize 1 kilogram of water. It's called the latent heat of vaporization, and that gives you that. And one can do that. And you can do this for anything. I could have said, like, how fast would I have to throw a penny and do this? And so essentially you have to heat the penny up to the melting point. Then there's an energy to melt it, and then heat, and then heat to bring the copper up to the vaporization point, and then amount to vaporize. And essentially all of it has to come from the kinetic energy.